Okay, let's get started. Today's topic is mechanical coupling. So after first introduction, we'll look at the governing equations. Of course, this is mechanics and electromagnetics, to be specific, the eddy current problem, taking into account motion-induced eddy currents now also. So to get the coupling that we have between those two physical phenomena, and highlight a few applications and show what is important when we do magnetomechanical coupled simulation. So to start off with the simple example where we need both mechanics and magnetic effects is, for example, this lift magnet. So we have a coil that introduces a current in the yoke, and the magnetic flux is closed through this air gap, and in this air gap we will have pole forces acting on, for example, an iron workpiece, and therefore moving it. And of course, if you move this, the magnetic domain changes. So here the magnetic flux is heavily governed by the amount of air gap you have here. And if the air gap changes, of course, the magnetic fields change, the forces, the mechanic forces change, and you have to adapt the geometry. So these are the two effects. We have magnetic forces on the mechanical domain that deforms and thereby changes the magnetic field. So challenges we can have here is, of course, both the sub-problems can be nonlinear. Magnetics can have nonlinear saturation effects. Solid mechanics is typically geometrically nonlinear if we have large deformations. And of course, other material nonlinearities can also be present. The magnetic forces on the mechanical structures need to be known, so we have to compute them, and we will see how this works. And if the mechanical parts move, the motional electromagnetic forces need to be known to be accounted for in the magnetic simulation. We have disregarded them so far. The other challenge is that the mechanics, of course, changes the configuration of the magnetic domain, so you have to, in some way, update the geometry. In particular, the air domain, which typically doesn't have any mechanical degrees of freedom. So if everything is mechanics and has displacement degrees of freedom, you can just use the displacement field to update the geometry. If you don't model the air mechanically, which you typically don't want to do, you have to find a way to update the geometry. And this is the last point, so that the mesh deformations in the air domain have to somehow be handled. And the basic phenomenology we use here is described in Manfred Kaltenbacher's book. So if you want to have more details, you can read up there. So just to remind you, mechanics, we have the balance of momentum as our governing equation. We have unknown displacements denoted U, and we have a loading term on the right-hand side. So this is a force density in general, and this comes also from the magnetic forces. So they can be contained here. And typically the boundary traction, so at the mechanical boundaries, we can also have forces, and they should be known or come also from magnetics. Then we have the stress tensor here, where our material law enters via a constitutive relation that can in general be nonlinear. And in the linear case, we have the linear strain displacement relation with the common B operator that relates our displacement field to our strain field. Yeah, but in general, everything is nonlinear. For the sake of simplicity, we can linearize here. Okay, and then we need Maxwell equations for the magnetic problem, but we need them in moving media, because now the mechanical domain, it can deform, it can move, and this has to be taken into account. in general, Maxwell equations are, of course, valid in any inertial frame. So you can either take the frame of the moving material or the stationary lab frame. That doesn't matter, but Maxwell equations, you have to be a bit careful with frame independence. They are apparently asymmetric. So depending in which frame you formulate Maxwell equations, they look a little bit different in structure. So this is a very funny thing to observe, and it actually might have sparked the development of the special relativity theory by Albert Einstein. So if you read the introduction of his paper to Electromagnetic bewegter Körper, you see this moving conductor and magnet problem mentioned. So here, discrepancy is you consider you have a moving conductor which moves with stationary velocity through a stationary magnetic field. If you look in the magnet frame that produces the magnetic field, then the moving charges in the conductor experience a magnetic force. So this is the magnetic force from the field. They have a velocity and the magnetic force is Vxp. However, if you look in the conductor and you move with it, the magnetic field never changes. And what you experience is, so to say, an electric field, and the charges feel this electrostatic force Q times E prime. So this is a very curious phenomenon, and it's sort of described by the Lorentz transformation. So we can consider the quantities either in the moving material frame that moves with our conductor, or we can write it in the stationary lab frame. So here, everything with the prime quantity is seen in the moving frame. And then you have certain relations that tell you how position, time, and the derivatives actually transform when you switch frames. And this is governed by the Lorentz factor. So you here see the common ratio of the velocity with the speed of light. So these transformations get important if you approach the speed of light, which typically in our engineering fields we don't really do. But still, so this is the basic or the governing equation, so to say. What you also see here, if you look a little bit in the transformations, I've written them down. It's not that important that you know all of those by heart. But the funny thing is that the transformations sort of make use of splitting the quantities in normal and parallel components, something that is similar to what we've seen with the interface conditions in electromagnetics, so that normal and parallel components are important here also. So for lower speeds, the Galilean transformation is typically all we need, but also here we have a few quantities that do transform, and one of them is the electric field, and this is the effect we've seen already with this moving conductor problem. So here the position, so to say, transformation is the one that we are used to if we have one frame of reference that is moving and the other that is stationary. We can of course transform the positions by using the relative velocity of the frames and so forth. And here the time derivative also gets this common, so to say, convective term. Okay. One thing important to know when we are dealing with electromagnetics now is that the Galilean transform can deliver two sets of equations. However, they can't, you have to, they're not both valid at the same time. One is valid for the magnetic quasi-static limit, so where magnetic fields are more important, and the other one is valid for the electric quasi-static limit, where the electric fields are more important. So both sets of equations are correct, but only handle the respective special cases. So this is the thing we need when we have eddy currents, and this is the thing we need typically in MEMS devices where we have strong electric fields that interact with the mechanical deformations. Okay, so we're interested in the eddy current problem, and we want to formulate it for moving media. So how do we do this? Just the general statement at the start. So Maxwell equations, they can be written in a covariant form. So that means they are structurally the same, no matter in which frames you formulate them. But you have to do this using these, I think they're called 4 vectors that also contain time. And then you have them structurally similar, no matter what the frame. What we do now to derive the eddy current problem for moving media is we consider them in the lab frame. So this is convenient for us, not in the moving frame. But you have to take into account that for the material relation, so whenever you want to apply Ohm's law, you actually have to formulate the equations in the moving conductor's frame. Otherwise, this is not correct. And this gives this form. So divergence B, we had this, the curl of E is so the law of induction. And finally, the Ampere's law we write in the moving frame, because here we have the free currents. These are the eddy currents where we want to apply Ohm's law in order to bring in the conductivity in the equations. And there then we have to use, of course, the electric field also in the moving frame, so the E prime. And here we have from the Galilean transformation the field in the lab frame plus the motional EMF term Vxb. And if we do this and we introduce our common vector potential, again, we see that we get this form of the equation where we have the usual curl term, the impressed current density, the usual time derivative, and an additional motional EMF term with Vx, the curl of A. And yes, the potential was as usual. Take care that this formulation is only valid for known and constant velocities. So the velocity is not time dependent, and specific fixed domain configuration. So if the domain configuration, of course, changes due to the thing that is moving through, you can't simply use this formulation. You need to take the domain update into account in an updated Lagrangian formulation, as you do it for mechanics with large displacements, for example. Okay, so let's look into, so to say, the importance of the velocity effect. And one way to quantify this is the so-called magnetic Reynolds number. We have seen beforehand, we go back to the equation, we have now with the velocity term a sort of convective term in the equation. So beforehand it was purely diffusive with a single time derivative, and now we also have a convective term in the equation. So even the stationary problem without time derivatives becomes a convection diffusion equation. And to quantify the importance between the inductive and the diffusive effects, you can use the magnetic Reynolds number. So it's defined by the material parameter, so the diffusivity effectively a reference length. So this is sort of the problem dimension or the characteristic dimension of the problem, and the velocity. And based on the value of the magnetic Reynolds number, you can say if advection, this is an advection dominated system for small magnetic Reynolds numbers, or it's diffusion dominated for large magnetic Reynolds numbers. So I've computed an example here. Just consider an object moving at 1 meter per second through your magnetic field, and one time the object is a copper wire with 1 millimeter diameter, and there we have a magnetic Reynolds number that is smaller than 1, quite a bit smaller than 1. So there you see that the velocity is actually the important thing. Whereas when you take an electrical steel sheet, so with a considerably higher permeability here, so mu, the conductivity, of course, is a bit lower, but still you get a magnetic Reynolds number of 100. So here, eddy currents will be more important in this case. Okay, so now we have this object moving through our domain. So of course we have to sort of take this motion into account. And one way to formulate the problem in an updated Lagrangian form is to derive this first. So this is done by writing out the differential quotient here with delta x and delta t's. So just expand this and then do a Taylor expansion. And what you see here then is that you can obtain this typical expression for the substantial time derivative. So this is the partial time derivative plus this convective term that is added. So you can now formulate the eddy current problem in the Lagrangian description by using the substantial time derivative. So that here are the steps. Insert the material derivative into the governing equation. The next step is to use the vector identity. So you can write this double curl or this double cross product with the curl, cross product of the curl as this special gradient operator, and the subscript A denotes that the gradient operator is only working on the A, not on the V. So the gradient of V is not, the derivative of V is not applied, but only on A, and again V in a gradient. So this is another differential operator then working on A. So this is basically just a rewrite using vector identities, and then you obtain this form that you can then use for this updated Lagrangian description. So basically you evaluate the time derivative as a substantial time derivative, so meaning in the lab frame, and you have this additional convective term that changed form a little bit. What didn't change is that this convective term is always 0 in 2D. So in 2D you can say, okay, my object is moving from left to right, so it has a velocity in the 2D plane you consider, and we know already that the A field for 2D problems is out of plane only, so they're always perpendicular. So here the convective term is always gone, and the motional EMF effects are contained here in this substantial derivative. We also have a special case where we have, so to say, eddy currents without any changing or alternating magnetic fields. And they can be introduced by the velocity. So velocity induced eddy currents. So we can actually solve such problems by considering a steady state problem, depending that the domain doesn't change. And typical examples for this are, for example, eddy current break. If you consider the rail that is moving with respect to your eddy current brake that is you typically mounted on the train, introducing a magnetic field, then the geometry, magnetically, the geometry never changes because the rail is just moving with the constant cross-section and constant velocity through the considered domain. So there's no domain changes, but still there will be eddy currents introduced due to the motional effects, but we don't need to consider any time derivatives. Other examples are maglev trains, so Magnetschwebebahnen, or a nice example is a magnet dropping through a copper pipe. You can look it up on YouTube. I have the link in the slides. It takes surprisingly long to come out of the pipe again because the introduced eddy currents actually have a reaction force on the dropping object. So in this case, we can use the static A-formulation with time derivative set to 0. One should think so, but you have to be careful because it doesn't satisfy the current continuity at conductor air interfaces. So here, when we have a conductor, of course, there should, and it ends, there can't be any current going out of it. So J in N needs to be 0 at the conductor. And now if you write in the pure A formulation, the expression for J, you know that this is gamma times E plus E is modified with the velocity term. In the A formulation, the E is purely dA over dt. So if we drop the time variation, because we said this problem is purely static, we end up with only Vxp in N. And if you take the triple product rule for the cross product and the scalar product, you can reformulate this and you end up with Vxn in B. That should be 0. And that basically forces, so to say, the B vector to be orthogonal to either the normal vector or the velocity. And this is simply not possible in the general case. So in this case, you need to use an AV formulation to get correct results. You can get correct results in 2D. So in 2D, we have Vxn, which is 0, because in this case, so to say, the velocity goes like this. The normal vectors are somewhere in 2D, but always need to be orthogonal to the velocity. Otherwise, the material continuity can't be satisfied. And then B can be arbitrary, and this still says 0, so this is fine. But in 3D, one has to be very careful that the pure A formulation is not correct. In fact, there are, so to say, a family of AV formulations that are possible for this problem. And one example I've given here in the reference, it's already a rather old paper, but still, I hope, valid. Okay. Another important thing for this kind of problems, whenever you have convective terms, you can encounter numerical instabilities. And this is common for all advection diffusion problems. So for large velocities, typically you get unphysical oscillations in your solution if you don't use any stabilization techniques. And this can be predicted by the element Peclet number, which is in fact very similar to the magnetic Reynolds number, because it sort of has a represents a balance between diffusive effects and the advection velocity. So if you have element Peclet numbers larger than 1, you will likely get numerical problems or instabilities. So H is the element size, velocity enters, and the diffusivity. So the material parameters for magnetics enter. There are various stabilization techniques. The simplest form, standard upwinding. So basically, you have to modify your ansatz functions depending on your velocity to take the convection into account. There's artificial diffusion, streamline upwind Petrov-Galerkin schemes, and many more. This is very similar. So the model problem for this is, of course, the heat equation with convective terms, so the classical advection diffusion equation. So in order to now bring the two problems to interact with each other, we'll have to look at the interaction effects, and one of them is the electromagnetic forces. And the basis for the electromagnetic forces is the Lorentz force on the individual point charges. And this for us, of course, has to be transformed into the continuum setting, because working only with point charges is not really handleable. Especially for highly deformable media, the magnetic material parameters might be deformation dependent, but this is something we will neglect at this point. But be aware that this can happen. And gradients in material properties can give rise to so-called Korteweg-Helmholtz electric and magnetic force densities. I have also a reference here if you're interested in these effects. You can read up on those in the reference. So let's go back to the Lorentz force, which is the basis. So for a point charge, a moving charge Q moving with velocity v with respect to the electric and magnetic fields experiences a Lorentz force, which has these two parts: the electric field that acts on the charge and the magnetic field that also has a force on the charge. And in the continuum description, of course, the force becomes a force density and is written in a similar way. And if you now then introduce the material relations we have, so for B and for E, you can expand this formulation and see the different components that the force density in magnetics can have. One, for example, is you have magnetizations. So a permanent magnet will experience a force density. If you have currents in a wire that are known, or eddy currents, you will have the classical Lorentz force JXB, and also polarization currents can lead to force densities. Yeah, so if the magnetization is piecewise constant, this gets difficult to evaluate, so this is one important aspect here. The other aspect is that the force distribution actually predicted by the Lorentz force can be incorrect, although the total force is correct again. So if you have highly deformable structures, the Lorentz force might be not the ideal force. You can reformulate the force density in terms of the Einstein-Laub force. One reference is here that describes this more in detail. Overall, so it's equivalent to the Lorentz force. So the Lorentz force is not wrong, but for highly deformable structures, it might make a difference in, of course, the deformation field that you would encounter. Okay, now we've seen there are a lot of components to the Lorentz force. Not all of them are typically technically relevant. So we now restrict ourselves now to magnetic forces that are often relevant. Typically, we have electric problems, all the electrostatic parts we neglect in this framework. And we can note that current densities can either be the impressed ones or the eddy current densities that we compute. And also the magnetization, typically it's only present in part of the domain and not in the whole domain. So let's look at the few selected ones. So the magnetic field can produce volume force densities, and they can be written like this. So you have here the standard Lorentz force. The J can be either impressed or an eddy current. So this gives you a force density, the Lorentz force density. And this term here actually gives you the so-called pole force that only acts in regions where we have permeability jumps. So if you either have a spatially varying permeability, typically that's not what we use in finite elements. We say permeability 1 in one part of the domain, permeability 2 in another part of the domain. So you have actually here the gradient becomes a jump, and the force only acts not as a volume force density, but as a so-called surface force, as pole force at the interface between, for example, an iron and the air part. What we also see is now we have magnetic quantities J and B. They both come from the magnetic solution or the solution of the eddy current problem, and the mechanic force density now depends on in a quadratic manner on the magnetic field solution already. Because J, for example, J and B are just derived quantities of the magnetic vector potential. That's our solution variable. So even if the magnetic problem is nonlinear, the coupling is linear. The coupling for sure will be nonlinear simply because of this quadratic nature of the coupling term force density. And that's why usually you don't formulate this in a monolithically coupled sense. But in an iterative way, you compute magnetics, you apply magnetic forces to the mechanic system, you compute mechanics, and iterate until you have convergence. Okay, before we can iterate, we have to compute magnetic forces. And one way to do this is to derive them via the principle of virtual work. So the idea is here we have magnetic energy, and the variation of the magnetic energy needs to be equal to the total virtual work done by the magnetic forces. And by this you can then express derive the expression that I've given beforehand for the Lorentz force. And the main steps I only give you here. The details are in Manfred Kaltenbach's book in the reference here. So you have to start from the magnetic energy densities for linear materials for simplicity. Assume isotropic material parameters. Do the variation, and then that's a bit of a tricky thing to rewrite this term to obtain the JXB expression. The other tricky part is, so to say, the evaluation of the pole force. We've seen we had the gradient of the permeability in there, so gradient mu over the material interface. So the idea is to transform the force density into a surface traction that we can then evaluate over the surface. And I'll just highlight the steps here. So we consider a small material cylinder with the axis along the normal direction of the interface. So basically a thin slice with one part in region 1 and one part in region 2. And then you can compute the total force by integrating the force density. And what you find out is that it only depends, so to say, on the permeability jump between the regions. So let's look here in detail how to solve the relation. So you can rewrite this spatial, so to say, integration in a du, so change of the permeability, and by this you transform the spatial bounds also in bounds in u, and this is how you see that the permeability jump is what matters for the force. And of course you still have to integrate h in h, and this again, as we've seen multiple times in magnetics, you do conveniently by splitting in normal and tangential directions. Now the tangential vectors denote t here, normal vectors n. So ht is the tangential and hn is the normal component. So you do this for h, and you can do this for b. And if you then insert this and rewrite h and b in terms of the vector potential, which is actually what you have to consider because it's your solution variable, then you see that you can write h in h as b normal squared over mu squared and h tangential squared. Okay, and then you can integrate and assume that the normal component of B needs to be continuous over the interface, and the tangential component of H has to be continuous over the interface. And then you can finally find the force density, which depends on the values, so on the permeability jumps, one time in an inverse manner, one time normal, and one time, so to say, weighted by the tangential field component and by the normal flux component. Okay, what you also should consider that pole forces always points from the regions with the larger permeability to the region with the smaller permeability. So no matter the magnetic fields, so to say, it pulls the iron to the magnet, so to say. You can compute the force also via the principle of virtual work. So this is an alternative way, which I will not go very much into details, but the principal idea is that you consider the elements around, so to say, the permeable part, or the, so to say, the deforming part. So you have to integrate the volume elements, and then you see that virtual displacement leads to deformations of the surrounding finite elements, and with this you can do the variation. And again, you have the okay. So the work done is the magnetic forces now on the so the magnetic volume forces in the location vector, so the deformation vector, and this you relate to the magnetic energy density And if you pull through the derivation, you see you can compute the total force at the interface, go through, so to say, the derivations, and by this you can obtain nodal forces for each node, if you do this in the sense of the finite element discrete distribution. Okay, now we have computed the forces. No matter which principle you use for this, you get a semi-discrete finite element formulation for mechanics. This is our common mass matrix, damping matrix, potentially a stiffness matrix, which is typically non-linear, though this is why it depends on the displacement u. And you have right-hand side forces. And the right-hand side forces depend on the magnetic vector potentials, either from the next time step, and they can also depend on the time derivatives of the magnetic vector potentials. In effect, this is the solution of the magnetic system, of course, and the magnetic problem now has a mass matrix. So these are the conductivities, and the stiffness matrix. So this is the curl term, and they both depend on the mechanical configuration due to the updated Lagrangian formulation. So the mechanical configuration changes taken into account there, and we have right-hand side forces for the magnetic. So this could be known currents, but if those currents are in the sort of mechanic region that can also deform, we also have here this dependence on the mechanical field U. Okay, so a lot of coupling terms here, which brings me to the idea of the iterative coupling in each time step. So the computational scheme is as follows. We have typically first to compute the magnetic fields, because if we don't do them, we don't get any mechanical loading. So this is the natural first step. So compute magnetic fields, possibly non-linear, iterate until you have convergence here, compute magnetic forces and apply them to the mechanical field. And then again, this is a mechanical problem, potentially materially or geometrically non-linear. So iterate until you have convergence of the mechanic subproblem, and then you update the displacements which change the geometry of the magnetic problem. And so this outer loop you have to again run until you have convergence here, and only then you can go to the next time step in order to do time-dependent problems. Now, there's the question, what stopping criteria do you use for the coupling condition? So you need something suitable, and it makes sense to use some kind of relative norms, for example, on the displacements. So here, the K indices are for the iteration of the coupling routine. And so you can say, okay, if the previous iteration and the current iterations of K plus 1 minus K, they are small in comparison to the current iteration. I haven't updated a lot the displacement, so this is probably converged. So you need some delta here to compare to. You can use relative norms also on the, for example, magnetic forces or other coupling quantities. This depends a little bit on the problem, but if you're converged in one, you should be converged in the other. Perhaps not to the same level, so to say. You can also combine several of these criteria. So you can say, okay, I want to iterate forces up to 10 to the power of -3 and displacements up to 10 to the power of -6 or something, and use a set of convergence criteria if you want. If you actually want to implement it or use this, there's a lot of implementation in openCFS, so we can do nonlinear eddy current problems. We can compute magnetic forces, so Lorentz and pole forces are currently implemented. You can solve nonlinear mechanical problems, and you can do iterative coupling between the fields via various tolerance criterion. You can also account for mechanic deformations in the magnetic problem by using the updated Lagrangian formulation that I presented previously. And you can use recently the mesh smoothing technique again that takes care of mesh deformations in the air domain that don't have any mechanical deformations. Just to highlight this a little bit, there's one slide. So typically, when we have this lift magnet example, we have mechanic deformations, for example, in the lifted workpiece. So at this interface, we know mechanical deformations. So here we can update the geometry straightforwardly by using the displacements we compute. But what happens actually to the air? Here we don't have any mechanical deformations. So as soon as, so to say, this deforms more than half an element, these elements get very distorted and probably quickly will have negative Jacobians, and this is not really what finite element codes like to compute with. So what you need to do is you need to smooth and adapt the mesh of the air domain, and this can be done by solving a pseudo-mechanics equations there, or a simple Poisson problem if you like. And in this sub-problem, you can apply the displacements here at the boundaries that you have computed, for example, from the real mechanical problem, and thereby get a nice transition of the mechanical deformation. So here I have a visualization. So if you use this technique, you get this sort of smoothed mesh that deforms like a mechanical structure would. The advantage of doing this in two different problems is that your mechanical sub-problem stays better conditioned. If you would imagine, okay, I take the material properties of air and of steel and I put them into the same monolithic system matrices, you get very low stiffnesses of, so to say, the unimportant air region that can destroy the conditioning of the mechanical system you actually want to compute. This is the reason why splitting this into two different PDEs is an advantage. Yeah, finally,